Hello, and welcome to today's calculus lesson. We're going to look at a problem from section 4.4, problem 47 from the text, and we're going to be given graphs of a first derivative and of a second derivative. And we're going to find the critical points and inflection points of the function. So note the graphs are of the first derivative and of the second derivative. We're asked about the function. The intervals on which f is increasing, which means your answer will be in interval notation, and decreasing, and the intervals of concavity. So the phrasing of the question helps you know what form your answer should take. Then they want you to sketch a graph of f, assuming that f of 0 equals 0, or that the graph goes through the origin is what they're telling you. So what I see we start with is we have to look first at a graph and see what we have a graph of and how it's set up. The red is our first derivative. On my screen, it looks like a bluish green, or greenish blue, is the second derivative. Now go back and reread the question. It's a completely complex question. There's many, many parts, but it doesn't read that way. So first they want us to find the critical points. And then they want us to find the inflection points. And then they want intervals of increasing and decreasing, and intervals of concavity, and then they want us to make a graph. So we have to create something. We got to make some lists and create something. Now, I want you to justify your work when you answer a question like this. If there's one of these on the final, I expect it to be justified. It's a good summary question. It makes a good type of question for a final exam, actually. So the first thing is critical points. As I scroll down here, I've made a list. I need to know where the critical points are. Well, critical points occur where the first derivative equals 0. That would be the first piece of justification you would write for work. And then you're going to go look at the graph and say, okay, I have a critical point here, critical point here. So first derivative equals 0, where the graph of the first derivative crosses the x-axis. It looks like I have a critical point at x equals 1 and at x equals 3. Then inflection points. Inflection points possibly happen where the second derivative equals 0, but it also has to change sign. Otherwise, it's not actually, it has to cross to the other side of the axis. Otherwise, you haven't really changed sign. That's not going to be an issue with this problem, but if the second derivative just touched and turned, where it's 0 would not be an inflection. Don't worry about that too much. It's kind of a technicality. But potentially your inflection points all occur where the second derivative is either equal 0 or non-existent. And the same thing with the critical points. Or does not exist is the other piece of justification. Or does not exist. But in DNE is the abbreviation for does not exist. So in the case of these graphs we're given here, that's not an issue because the first derivative and the second derivative are both continuous, so they exist everywhere on the interval shown from 0 to 4. So I'm looking at the second derivative for this one, and I should probably take a different color to try that. We'll do that in blue. So I'm looking for zeros of the second derivative. I really can't say if 0 is an inflection point. If you wrote it, I wouldn't mark it wrong because I can't tell if it changed sign. And we're only looking from 0 to 4, so I have a 2. And I have, well, maybe I have a 4. For now, we'll just assume this goes on and we'll say 0, 2, and 4. That may or may not be great mathematics, but certainly you would want the x equals 2, and then possibly the 0 and the 4. The justification is, well, actually this and this. And you could note that if you forget that, that won't be a big problem, particularly not for this problem because you would have to have had, if the second derivative had gone up and then back down, that would be an issue, but it did not do that. Intervals where f is increasing and decreasing, we're going to go back to our other pen because that comes from the first derivative is positive, which means the first derivative is greater than 0, just the other way to say that, or it's above the x-axis. Those all mean the same thing. So it looks like from 0 to 1, and you're not going to include the 1. I think my math lab does have you include the 0 is the endpoint, I won't be fussy on the end, whether you use a square bracket or a round parenthesis there. So from 0 to 1, the first derivative is clearly above the x-axis. And from 3 to 4, and that will be the same case. The 3 will not be included because you're at 0 there, and that's not above the x-axis. But the 4, I suspect MyMathLab does that. But if you did a round parenthesis, I would not mark that incorrect. What I'm looking for justification is to see any or all of these. Now, decreasing, again, is a first derivative question. Increasing and decreasing, a function increasing or decreasing comes from the first derivative. So the first derivative is negative, or the other way to say that is less than 0. Or the other way to say that is the graph of the first derivative is below the x-axis. And we have the graph, so that's actually the relevant one for our question. And when I go back to my derivative, I see that between 1 and 3. And I would not include the n's because at 1 and 3 we're on the x-axis, not below it. So there is my interval where my function is decreasing. Now, intervals where f is concave up. I'm going to change my pen to indicate concavity comes from the second derivative. Whether it's shaped like this, which is what we want for concave up, or like this for concave down. That would be the shape of the function if it's concave up. That would be the shape of the function if it's concave down. So I want the second derivative is positive, so I'm going to look at the blue graph. It is greater than 0, or it is above the x-axis. And when I look at that blue graph, that looks like from 2 to 4. And MyMathLab will probably include the 4. Nobody will include the 2. I will not argue with you. I will go through any answers you have on a test or quiz and make sure that if you put a round parenthesis, that you got credit for it. Concave down is just what you're thinking. Hopefully you're a step ahead of me and you're seeing this now, is where the second derivative is negative, or less than 0 is the other way to say that, or below the x-axis in the case of a graph. So that would be, if I look at my graph, from 0, and you may or may not include the 0. I think this is the way MyMathLab does it, but I could be wrong. It could be they're looking for a round parenthesis there. I won't care about whether it's square or round. I just want to see the correct interval. And I want to see, what I want to see is this justification. You just show me that the second derivative is what we look at for concavity, and either that it's negative, less than 0, or below the x-axis. That is proper justification for picking out the concave down interval there. Now, I've done all this, and I'm asked to sketch a graph. And I am also told that for my graph, f of 0 is 0. So they give me a point to cross through. So I'm going to sketch my graph over here. This is going to be a graph of f of x. And your answer may vary a little bit. If you see this online in your homework, it's probably a multiple choice. So you can do this by eliminating possibilities as well. And I know this only goes from 0 to 4, so I only have to draw my graphs from 0 to 4. And I'm told that I have a point at 0, 0. F of 0 equals 0. That's this point right here. And I'm just going to kind of mark off 1. I could actually have drawn it right on top of the other graph, but I feel like that would be confusing for you to watch. 4. Now the 1 could be a little closer. It's not drawn to scale, certainly. So, from 0 to 1, my function is increasing, so it's going up. But from 0 to 1, I'm going to draw a dotted dashed line there. From 0 to 1, my function is increasing, but it's concave down. The second derivative is, so increasing and concave down looks like that. That's what a piece of increasing and concave down looks like. So I'm going to draw that from 0 to 1. And it doesn't really matter where I end it. That's kind of approximately right. And yours will be approximately right if it's kind of that shape. Then what happens at 1 is I stop increasing and I start decreasing. That gives me a relative maximum. So this is going to be, this point here is kind of going to be a top. And then I start decreasing So my function's headed down, but it's still concave down, so it's still bent over in the same direction. And that continues, it continues decreasing until 3, but until 2, I'm bent down. And then I'm decreasing and bent up. So let's just go to 2. So I go to, and I don't have to go all the way back to the x-axis. It kind of looks like it does that. I go to x is 2, and then I keep going down, but watch, I'm going to turn this a little, because now I'm concave up. See, it makes a bowl shape like this. And I'm concave up all the way to 4. So I'm always going to be twisted upward as if I could hold water. But what happens at 3, so at 3 I see I've got another change. So at each of these places where either the first or second derivative crosses the x-axis, I've got some shape to change. First derivative, let's make a little chart. First derivative, second derivative. And here's the shape of f. If the first derivative is positive and the second derivative is positive, that means your function is rising and concave up. If the first derivative is positive and your second derivative is negative, it means your function is rising, but you're concave down. So see, the function still goes up. If the first derivative is negative and the second derivative is positive, your function is going down, but your concavity is up. If your first derivative is negative and your second derivative is negative, your function is decreasing and you're concave down, so you're turned over that way. Those are really the 4 pieces you're trying to put together. So from 2 to 3, I see my first derivative is negative and my second derivative is negative. So I've got this shape where my function's heading down, left to right, and it's, oh, wait a minute, did I do? No, from 2 to 3, my first derivative is negative and my second derivative is positive. It's above the axis. 2 to 3, I'm going down and I'm shaped so I'm concave up to like an upright U if I finish the other half. From 3 to 4, both the first and second derivative are positive, so I have this shape here. And kind of goes like this. And if you did not make yours go exactly through the x-axis there, that would be fine. Start there. If you had started here and gone up, let me do it in a different color. Are there other things that would be fine here because we really can't tell entirely, although the graph looks pretty symmetric. If you had done something like this, as long as you made a max at 1, because that's where the first derivative changes sign. And then if you had done something like this, it would have still been okay, more or less, although you still need a min at 3. I kind of didn't do that. I would have needed to go down to 3 and then back up. But if you didn't cross I really don't know where it crosses the x-axis, although these look pretty symmetric. I think what I've drawn in the black-colored curve is correct. But the big point is, how do you justify? And then if you're choosing a graph, this is much easier than drawing it, because they won't give you both this black one and this blue one. You'll have one right choice, and all the other choices will violate one of these shapes. So figure out what shape each part should be and pick the graph that matches that. But your justification, if you're showing work, needs to be all of these things I've outlined here. All right, I hope that is helpful, and email me if you have questions. Thank you for joining.